So as I said, we're looking for the expression for the solubility product, sometimes called a law of mass action. And just as we talked before, Ksp is the same thing as Kaq. So Ksp is equal to the products over reactants, and there is my products. There are the ions. And we put them in brackets to show concentration, because an equilibrium expression or the law of mass action is essentially a rate law of some sort. And of course we have an f to the negative 2 squared. That coefficient becomes the exponent. Okay, we're relating the rate of the forward equals the rate of the reverse. This Kaq is really, by convention, the rate of the forward over the rate of the reverse to tell us who's favored when these concentrations are constant. Okay, so in any case, they wanted you to write the expression for the solubility product, and that is what we did. And we call it a Ksp because it's for a particular ionization reaction. They all look very similar. There's no reactant because this is a solid. Solids are not considered in part of the expression because solids do not have a concentration. Concentrations, like a molarity, which these brackets represent, cannot be had with just a solid. A solid is not a concentration, it's just a solid. There's nothing mixed with it. You probably could make some case for an alloy, but that wouldn't change in a reaction. Aqueous or gases have concentrations. Solids and liquids do not apply. So I would always say the products over the concentrations of the products over the concentration of the reactants, coefficients become exponents. Solids and liquids don't apply. And that would give us the expression. Now this is the formula for this reaction that will give us a value that would tell us who is favored at equilibrium. Now they want to calculate its value. They're giving you a temperature because these equilibrium constants are temperature sensitive. If you change the temperature, you change that position of who's favored, one way or the other. Okay, so any case, what they're saying is that we have some information here. We have a concentration of the Mg plus 2 to be 1.21 times 10 to the negative 3 molar. Okay, so that's a concentration. And I can plug that in right away. So I know my Ksp in this area is 1.21 times 10 to the negative 3 molar. That's my concentration for my Mg plus 2, right there. Now the question is, what do I use for my F? Now I know the Ksp. I'm trying to solve for the Ksp, so obviously I need to know the value of my F negative. Now if you look at the stoichiometric relationship here, you'll see that for every one Mg plus 2 that is dissolved, 2 is produced. So if I am at equilibrium, okay, and I know the concentration of my Mg plus 2, it's staying constant, the rate of the forward equals the rate of the reverse, then this concentration has to be double. 2 fluoride ions per every 1. So if I know the concentration of this, this must be twice as much, because for every one of these, there's 2 of these. So it's double. Okay, so you can make this 2.42 times 10 to the negative 3, and that's double. And don't forget the square. And let's go find that value. So I'm using my TI-84, if you are too. I don't have the silver or platinum edition, but hey, I'm not as cool as you. 1.21, second function, I'm doing negative 3, and I think I'm going to go square 2.42 first. 2.42 times 10 to the negative 3, okay, because I just doubled that because it's twice as much. I'm going to square that, and I get 5, and then I would take that and times that by 1.21 to 10 to the negative 3, and I get my Ksp to equal 7.09 times 10 to the negative 9. No units for Ksp. So look at that. We got 2 points in this problem. We got the expression and we got the value. Understand this was a 2x. Now you may say, Mr. Grazi, what do you mean by 2x? Well, when we do our equilibrium problems, we look at our Mg plus 2, and we look at our fluoride ion, 2F, we know that for every one of these Mg plus 2s, 2 of these are made. So as we go from the solid, which I'm not going to write in here, to these, we know that this is going to be a plus x, and this is going to be a plus 2x. So if I know the value here, this would be twice as much. So you'll hear that designation. But let's look at this next problem. Okay? In this next problem, we're going to need an ice table, an equilibrium problem here. And we'll see what we have here. So in this next problem, we're saying that the concentration of Mg plus 2 in a liter of 1 liter of water of saturated MgF2 solution. Now, by saying saturated, they're screaming to me that this has reached equilibrium. We learned in class that in order to have a solution equilibrium, or a room filled of 100 people, you stuff one more person in it, you're going to force one out. So in order to have equilibrium between the rate of dissolving and the rate of precipitation, you have to have a solution that's saturated, holding the maximum amount of ions. So this is telling me that I am at equilibrium. Okay, I'm at a certain temperature. Notice that temperature is staying the same. They're not being sneaky, they're just covering all bases. Remember, this Ksp is temperature is sensitive. Okay, so I have a reaction. I have Mg plus 2. They want the actual concentration of this when it's saturated when I add some other compound to it. So when I build my ice table, this is the initial, this is the change, and this is at equilibrium. We want to solve for what this concentration will be at equilibrium. Okay, we know what the Ksp value is. And I know that Ksp, as we have above, is equal to the concentration of Mg plus 2, which we're trying to solve, so that'll be our unknown, times the fluoride ion squared. So we're going to know something about this, something we already know the Ksp, already solved for that, and we're going to solve for that value there somehow. So how do we do this? All right, well, initially, okay, initial conditions, how much Mg plus 2 do we have? Well, that's easy. Based on what we have here, okay, and we have 1.21 times 10 to the negative 3 molar. That's our concentration of our Mg plus 2. All right, and I probably don't need those brackets, so I'll just get those away. That's the molarity. Okay, and molarity is what we put in an ice table, in an equilibrium table. Now, how much fluoride ions do I have? Well, I know that I have twice that number, so 2.42 times 10 to the negative 3 is twice as big. Okay, that's what I have. Now, there's a little twist to this problem. And this twist is that I'm adding 0.1 moles of solid Kf to this problem. Okay? So if we do that, we are going to now understand that Kf is going to break apart into K plus and F negative. All right. Now, what does that mean? Well, that means that I am going to really be adding more fluoride ions to the mix by adding potassium fluoride. Now, this is a soluble compound, completely soluble because of that group 1 ion. And group 1 ions, of course, have a low charge density because they're big ions stretching a +1 over. So they're going to be very, very easily to separate, but water is going to get in that between that attraction and separate, as we've talked about. So K plus is also being added, but there's no K plus in this equilibrium. Okay, so my friends, K plus is going to spectate and not be a factor. This F is really, by adding Kf, you are really, by adding a common ion, really increasing this value here. So what they say is they have 0.10 moles in a liter of solution. Well, that's pretty easy stuff. 0.1 moles over a liter is 0.10 molar. Okay, easy. Notice they said the volume change is not significant, so that's what we're going to do here. So by adding a common factor, I'm going to add 0.100 m to the mix here. So I started out with this amount because I'm saturated. Okay, and I am adding 0.10 molar of fluoride ions into the mix here. Okay, the question is, if if you guys already figured out, my Q is getting a bit bigger than my K, right? We learned today, okay, therefore this reaction is going to go this way. We're adding too many products. This can only hold a combination of these two together that equals this KSP. I'm adding too many products, so this is not at equilibrium anymore. I now have more products, and if it's products over reactants, I'm not at equilibrium now. My Q is larger than K. Well, to lower the Q, reactions always go toward kelvins. I'm sorry, 2 Ks, no kelvins. All right? So it's going to go in the reverse. So we're going to be minus, okay, some value here. So this is minus x. And if you haven't already guessed it, this is minus 2x. That's the change. So the initial concentrations that we have are this value because it was saturated in this value. By adding Kf, we are really increasing the F negative by that much. So that's its initial concentration. Now, we know this reaction is going to go in the reverse because Q is now larger than K. And as we talked about, reactions always go toward Kelvin. I said it again, KEQ. So the reaction is going to go back. Okay? So because of that, it's going to go back some amount. How much? We're trying to find what this is. So at equilibrium, this is 1.21 times 10 to the negative 3 minus x. This one, okay, and I'm going to write this way, 0.100 molar plus this small number, 2.42 times 10 to the negative 3, okay, minus 2x. Now, if I put this value, and I put this value for F into my KSP formula, you probably can see that I'm going to have, okay, a quadratic. And that's not something that's quick to solve for, all right? You're going to have to factor all this stuff out. So the way to get around a quadratic with very small values of equilibriums, doesn't it make sense that this is not going to go back all that much? I want to talk about this for a second. We have just solved for what the equilibrium would be. Now, this KSP is a small value, which means it barely goes forward. We only have a little bit of ions here. Now, we just added a lot, okay, of fluoride ions as compared to what was in there. 0.1 compared to 2.42 times 10 to the negative 3 is really insignificant. So what we're going to wind up doing, and it sounds weird, we're going to basically take this away. Yeah, we can actually approximate this away to be insignificant. What we're subtracting is going to be small. We can't drive this reaction that much backwards because, well, only a little bit exists. This thing is barely soluble. It's not. It's called insoluble, and it has a few ions that do come out. So we don't have a lot of wiggle room to go backwards. This thing is going to go back, but it can't go back that much because it didn't go forward that much to begin with. Now, if you compare 0.1 molar of what we added to this small number, and if you don't understand, 2.42 times 10 to the negative 3 is really 0.00242. Add that to 0.1, what do you get? 0.10242. 0.1 and 0.10242, we're going to say is about the same. Okay, even though you say, well, it's different. Well, it's 2 orders of magnitude. It's 100 times difference. So this little bit, we can just say that doesn't exist. We can approximate it away. And therefore, it makes our math easy. KSP, which we solved for in the previous problem, okay, which is right there, is 7.09 times 10 to the negative 9. It equals, now we're not going to get rid of this. This is going to be a small number, but guess what? I want to know what that amount is. I want to find that x and see how this changes. So that stays the same. And of course, my F is just going to be 0.1. I'm taking away, and of course, don't forget squared, okay? And that makes life real easy. Again, this whole bit here, this number compared to 0.1 is insignificant, and the subtraction of even a tinier number, even a smaller number, okay, doesn't change this value significantly. So this gets all approximated away to make basically the question much easier to solve. And we do this all the time. Okay, this is a classic AP problem. So in any case, I solve for this, and what I get is when I square this and multiply it across, I get 7.09 times 10 to the negative 9, and I get is equal to 1.21 times 10 to the negative 5. I just times it by 0.1 there, squared it. Okay, and I multiplied across, and I distributed that across. So that gives me negative 0.01x. So for those that didn't know what I just did here, okay, I squared this. 0.1 squared is 0.01, and then I distributed that to the x and to that, and that's my new simplified version. Okay, now as I go across, I'm going to minus this number times 10 to the negative 5 to this side. Okay, and when I do that, I subtract negative 2. This is going to cancel, of course. Okay, but this will be subtracted by that, so that'll be negative 1.209. Okay, 29. Carry some numbers here, doesn't care. Times 10 to the negative 5. Okay, and all I did was subtract 1.21 times 10 to the negative 5 from that. Okay, now I'm going to divide by 0.01, all right, because I'm just solving for that, and that equals my x. And when I put that in my calculator, my x is equal to 1.209 times 10 to the negative 3. Okay, that's my x. It's not my answer, though. The answer wanted the concentration of Mg plus 2. That's 1.21 times 10 to the negative 3 minus x. So when you put this value back into this equation here, which is the equilibrium concentration, okay, and do the subtraction, okay, and I'll just write it out here for our viewing displeasures, I get 1.21 times 10 to the negative 3 minus 1.209 times 10 to the negative 3, okay, and that gives me 7.10 times 10 to the negative 7. And be careful, because those come out differently if you don't carry all these numbers at the end, 929. So if you do that, you will get this number, and that is the concentration. That's tiny. Look what x was equal to. We solve for x is 1.02 times 10 to the negative 3. So minus 2x, if you multiply this together by 2, 2.409 times 10 to the negative 3, and you subtract it, okay, from this, okay, and then subtract it, try to add it to that, that essentially is an insignificant, much insignificant. So it kind of makes sense that those small numbers wouldn't add that up. Okay, seems like a crazy amount of work, but you can see that it all follows through equilibrium. Okay, and I'm going to stop there, I believe. But I would like you to try this C here. Now, in number C, they want you to predict whether precipitate will form when 100 milliliters of a 3.00 times 3 molar of is mixed with 200 milliliters of this solution. And what you're doing here is, so you understand, you are going to mix, okay, two solutions. You're taking 100 milliliters of 3.0 times 10 to the negative 3, and that's magnesium nitrate. And you should all know that nitrates are soluble, so you really are adding Mg plus 2 ions into the mix. And then you're also adding 200 milliliters of a 2.0 times 10 to the negative 3 molar solution of sodium fluoride. And notice the temperature is staying constant, so we can use the same Ksp. This is also soluble, so you're really adding fluoride ions. Now, if you're pouring these together, Your new volume is going to be 300 milliliters. So before you do this problem, you have to figure out what the concentration of the Mg plus 2 is. It's not going to be this. It's going to get diluted. And how do we do dilution problems? We said Mv equals Mv. So what you do is to solve for the concentration of the Mg plus 2, okay, which would be right here. You know its current volume was 100 milliliters. And we know that its its new molarity, that'll be what we're going to solve for. The molarity that you had was 0.003, right? That's the same number as that. And we're going to solve for the volume, of course. We're going to solve for the new molarity when the volume now is 300 milliliters. So you can see that you're just going to solve for the molarity, the new molarity of the Mg plus 2. You can do the same thing for the fluoride ion. It currently is 0.002 molar, right, in 200 milliliters. What is its molarity when the solution is now 300 milliliters? So you're solving. Now, once you have the concentration of Mg plus 2 and F negative, okay, well, think with me for a second. Mg plus 2 plus 2 fluoride ions. Now we know that that's the reaction above. That makes magnesium fluoride, which is generally considered to be insoluble. Now, you have these concentrations. Well, guess what? Build your ICE table. ICE. Put these concentrations here for the Mg and for the F. Don't think about X at 2X. These are the actual values. This is not at equilibrium. So what you're going to do is you can actually figure out, without putting an equilibrium table together, even though I started to, just so you can see what's going on, evaluate your Q. Your Q is equal to what? Mg plus 2, okay, times F negative squared. So put these values. Sorry for the ICE table. I was thinking of talking you through why X and 2X, but it's as simple as plug these values in, okay, into your equation for Q. Give me a value for Q. Don't forget to square it. Once you have your for Q, I want you to compare it to your K, which is 7.09. And depending if who's bigger or smaller, tell me if we're going to make it precipitate or dissolve more ions. Okay, please do not do D. We're not ready for that yet. So try that for fun. Okay, hope this was enjoyable. See you later.